I just went to the website and I found out what the z-score is. I actually have a table that shows z-scores for different percentages. I'll put that table up here. So let's go to where it says 80% right here. The z-score that goes with 80% is 1.282. So this is 1.282 at this boundary down here. And actually down here, this would just be the opposite. It would be negative 1.282. Remember that when we were working with our last example, dealing with a population of 5 people, sample 2 had a z-score of negative 0.81, and sample 9 had a z-score of positive 0.81. And I said that 80% of the possible samples fell between sample 2 and sample 9, which means that in that example, the z-scores at the lower and upper boundaries of the middle 80% were negative 0.81 and positive 0.81. Because sample 2 at the lower boundary of the middle 80% had a z-score of negative 0.81, and sample 9 at the upper boundary of the middle 80% had a z-score of positive 0.81. But notice how when we're dealing with a sampling distribution that follows a normal distribution, the two z-scores aren't the same as what we had in our last example. In our last example, the two z-scores at the boundaries of the middle 80% were these two z-scores. But now the table is giving us these two z-scores for the boundaries. So the reason why these two z-scores from the table don't match these two z-scores from our last example is because the sampling distribution in our last example didn't follow a normal distribution. You can see that it doesn't follow a normal distribution with this green curve right here. So what this table is saying is that if the sampling distribution follows a normal distribution like this, then the z-scores at the upper and lower boundaries of the middle 80% will be these two z-scores. Now let's see what the table says the z-scores are at the upper and lower boundaries of the middle 60%. Well, it actually doesn't have them in here, but I think that I did. I think that I checked it online one time, and I think it said 0.84. I'll check that online on a website, and then I'll be right back. So I was correct. It's about 0.84. It's not exactly 0.84, but it's pretty close to 0.84. So I'll put that in here. It didn't give us 60% in the table right here. That's why I wasn't able to get the z-score for 60% from this table, but I was able to look on a different website to find it. So let's imagine that in this sampling distribution, 60% of the samples are between these 2 points. the z-score at the lower boundary of the middle 60% will be negative 0.81. I'm sorry, negative 0.84. And the z-score at the upper boundary will be positive 0.84. The z-score at the upper boundary of the middle 60% will be 0.84. So notice how the z-score at the lower boundary is the opposite of the z-score at the upper boundary. Sorry, I need to fix this. So if the possible samples, if the sampling distribution follows a normal distribution, then 60% of the possible samples will fall between negative 0.84 and 0.84. Now, in my last example, when we had this sampling distribution, 60% of the possible samples fell between these two z-scores, negative 0.41 and 0.41, because the z-score right here, where these two samples were, was negative 0.41, and the z-score where these two samples were was positive 0.41. So 60% of the samples fell between those two z-scores. In other words, 6 out of the 10 samples fell between those two z-scores. So the middle 60% was in here. And notice how these two z-scores don't match the two z-scores that the table gave us for these two boundary points of the middle 60%. The reason why the z-scores from our last example don't match the z-scores from the table is because these z-scores are the boundary points if the sampling distribution follows a normal distribution, which our last example didn't follow.